title of this lecture is Frequency Response Based Analysis and Design of PWM Converters, and the official name is, as I said, Dynamic Analysis of Power Converters, but this is more informative and more precise description about this lecture. Key word here is frequency response. Okay. All of you knows what is the frequency response applied to linear time invariant systems, circuits, LTI systems. So frequency response is well-known techniques and definitions and application of them. So during your undergrad course, you should learn that several times, repeatedly. Okay? But things here is we know and you know how to apply this frequency response method technique to linear time invariant system. But what you are dealing with this semester is not a linear time invariant system. That is this PWM converters, which is non-linear and the time varying system. So this technique you are familiar with cannot be directly applied this PWM converters. So there should be some bridge, filling gap in between. So that is the purpose of this lecture. By how to use this well-established frequency response techniques for the linear time invariant systems, how to apply it to the PWM power converters, which is non-linear and the time varying system. Okay? How to design, how to analyze dynamics of this PWM converter, and how to design the controller of PWM converter using this technique, which is only applicable to linear time invariant system. So we need to set up the bridge, build a bridge between them. That is called modeling. During the modeling process, this linear time invariant system, PWM converters, will be translated simple model to which this frequency response technique will be applied. Okay? So that is the main flow of this lecture. So after this lecture, you will be learning how to use your existing knowledge to this new PWM converters. Okay? So that is the idea behind of this course. So it sounds very difficult or formidable, but it's not that difficult. Okay? If you follow me closely, then you will get all the information and the knowledge applicable to any PWM converters. Okay? My name is Byung-jo Choi. I'm emeritus professor. Emeritus is just retired professor of this electrical engineering department of this school. So this is maybe probably end of 2 years after my retirement. I retired 2 years ago, about this time. No, not 2 years, 1.5 years ago. Okay, all right. Okay, kind of the syllabus. I skipped the all unnecessary decoration of that. So this is the key things about this course. This textbook is very important. So this book is very good compared with its price. Okay, I used several similar books. Actually, I wrote 4 books, and 2 of them is printed in America. So that is about 200 bucks. That means more than 20만 won in Korean. So you cannot buy it. Okay? So I wrote this version. This version is in English. This is also in English, but it contains the maybe 90% of that expensive book. Okay, at very low price. This is somewhere about 25 bucks. 25 bucks. Dollars. Okay, I don't know. That is 3만 or something. 4만 won in between. All right. So this is very, very cost-effective book. Okay, I strongly recommend to buy this book. All right. This is, I spend 10 years on this, and I spend a lot of time writing this and in drawing all the figures and preparing the exercise problems and preparing the solutions of that problems. Okay, so this is a good book. Okay, and first announcement is we move the 4 classes during these 2 weeks. So I have something scheduled in advance. So I should go somewhere to present something. So I cannot have class here. So we we just change this class schedule to this. This is after end of semester usually. This is makeup class period or exam period. Okay? So the classes during these 2 weeks can be transferred to this, or if possible, the classes will be given in 2 exam weeks. That means maybe I can hand out a takeout exam for midterm, and there is a 1 week for the midterm in the school. Okay, so maybe we will have a class for that weeks to compensate for this one. Okay, if that is impossible, then we have classes. 4 classes here. Usually, I end everything before this, before December or before June in general, okay, without skipping any classes. Okay, so that's first one you should know. And the grading policy, midterm test is 45 to 50%, and the final exam will be 45 to 50%. And other activities, class activities like homework and project and attendance will constitute up to 10% of your total grade. Okay, but I'm giving very good final grade. If you do your normal effort, more than normal effort, you will get the credit starting from A plus, A, 0, A minus. Okay? If you have B, then you assume you did very poor in the class. Okay? That is the general policy. My grading policy and office hour, I don't have any office, so there shouldn't be any office hour, but you can email me if you have any questions or any comment about the lecture or class, some questions, some doubtings, then you email me to this address with your returning phone number. So, okay? So I can call you, I can read your email, then I can call you to discuss about the content of your email. Or you can call me for anything, but somehow before calling this, you should have a prior appointment. Okay, maybe this email can be considered as this prior appointment. Okay, so this is my email address and this is my phone number. Maybe you need this. I have one homepage called EE Classroom. Classroom is there are a bunch of classes posted there, and EE means electrical engineering, but in that the focus is every course is directed towards the power electronics. Okay, so I'm using this electrical engineering, meaning this is the power electronics. Okay, and the address is this one, visit. Forget about visit. So eeclassroom.org is the address of my homepage. So that homepage is very important for you because this post-lecture slide and the post-lecture video will be posted through this homepage. Okay, you visit this, then the lecture slide and the lecture video, they are posted somewhere here. Okay, so you figure out there are many 4 subject lectures. It's not special topic, something else. I call it tutorials and workshops, books and sitemap, and you go here, then there will be a bunch of lectures, and I'll provide some guideline about the lectures. Okay. When you are logging on this, you can use any portal site and the internet site starting with HTTP something, but don't use the YouTube. Okay. YouTube, if you type this one, there are a bunch of garbage titled with EE something or class something. I did that. There are many classes about the kindergarten classes for the something like that. Okay. So if you use the Google portal and the HTTP internet gate, and then you can log on this, and you can see this. Okay, so this is me maybe 3 years ago, and there are many classes. So I'd like to introduce some classes in there for you. Okay, so this is my logo. This has some profound meaning, but I don't want to go the details about this. But it has many very important implications. All right. So topics in PWM power convergence. There are many other topics like electronics and something else. Maybe there are 20 classes posted there, but among them, this is the lectures related with PWM power conversion. So topics in PWM power convergence and the lecture videos posted in eeclassroom.org, and I grouped these lectures into 3. Okay, first one is component and the circuit of PWM converters. And second one is modeling, dynamics, and the control of PWM converters. Third one is DC power distribution systems. Okay. So in this topic, I lectured the component and the circuit of PWM converters. Component means power stage component, and semiconductor switches, MOSFET, and the diode. And this component, reactive component, inductors and capacitors and transformer. And that lecture was provided 2 years ago, 1 year ago this time. Okay, so there are old videos. So there are one Korean version lectured in Korean. That was for the senior student, undergrad senior student. That is the one you want to see if you feel you don't have enough knowledge about this component and the circuit topology of PWM converters. Okay, and the same material is covered here. Power conversion circuit. This is lectured in English, so this is good for the foreign or international student. Okay, and this is the book I wrote for this. So this book is fully dedicated for this. Okay, so if you are interested in this part, you can buy this book and you study videos of these lectures. And this one is just the components and circuit topologies of PWM converters. This is just the circuit analysis and study of the electric property of semiconductor diodes, switches, MOSFETs, something like that, and the circuit behavior of inductance and capacitance and transformers, not ideal transformers, practical transformers. Okay, this is very different from the things in electric circuit analysis you are learning in the sophomore undergrad student. Is something else. Okay, in that you are just learning the DC response of this circuit or AC sinusoidal response of this circuit. But this here you need to know this something about the transient behavior of this component as energy storage or energy transfer device. Okay, so for that, maybe you may consult this book. Okay, I wrote 2 books about this. So one book is the first version of something. So that is the out of print. Okay, you cannot get that. So this is the second edition. All right, but content of the first edition and most part of this edition, first part of this edition and this second part of the content, 90% of this book is condensed into this book. Okay, so this book is very good. Okay, this is the best book for this course. In this part, we will be talking about this modeling and control of PWM converters, and this is done in Korean. Okay, maybe the domestic student they can go this lecture slide in here, right? For the basics about this, or maybe same things, but I revised some content of this. Okay, so but this will be good, and this is the same thing, but this is for the foreign student. So this is done as the graduate lecture style. Okay, but basically they are the same. Okay, this one is more advanced, but basically the same. Okay, and this is one thing. Okay, they are all the lectures, this kind of lectures, normal lectures, and this is a tutorial. So I provide 3 hours tutorial, maybe 2 months ago in Jeju Island, and that is recorded there, just 2 hours, and I recorded additional 10 hours. So this is total 12 hours lecture long videos. So this lecture, this new lecture is prepared based on this. Okay, so for the Korean student, this will be very informative because the same, almost the same content will be taught here, okay, in English. Right? So this is very good. Okay, and another one is this. The most circuit analysis technique is in here. Okay, but some basics about the classical control theory is provided in this course. This was the senior course, undergraduate student, senior course, and this is done in Korean. So this will be good for the domestic student. And this is classical control theory. I taught this course in English last semester. Okay, so maybe some of you took this course. So content of this course, the title is control theory, but this is a little bit different from the classical, not conventional control theory. This control theory is oriented toward the power electronics for this class particularly. Okay, so if you took that course, that will be very helpful. Otherwise, you go to this course. Okay, the lecture video of this course and this one in English and in Korean. Okay, and this is the last one, DC power distribution systems. So I'm talking about the bunch of DC to DC converters connected together for one particular applications. For example, the data center, it requires all of DC power, and the bunch of maybe 100,000 of connectors are all connected, interconnected in parallel and in series, and some filter stage in between. So very complex system. So this topic deals with how to analyze and how to design those kind of system. So what kind of a problem is there and something like that. So this is considered as advanced, but not difficult course. Okay, this course probably this will be offered next semester for the graduate student. Okay, so this is outline of the lecture videos in this homepage. Okay, this site. All right, so try to visit this site. Okay, this is the content of this lecture. So part 1 goes about 250 pages. Okay, we have so many topics: open loop bug converter, closed loop bug converter. We start out from the beginning. Okay, I know there are many students, undergrad students, taking this class. Okay, and I know there are some students not majoring electrical engineering. But I know some students not exposed to the subject of power electronics, not at all, something like that. Okay, but we need have the same basis. So I want to make sure you are in the same boat. Okay, for that, I'll spend some time about this open loop bug converter, closed loop bug converter, and this one is also basic things. Okay, this is kind of repetition of the previous course, but somehow I decided to go through this. Okay, for the common basis of all my students. So we are in the same boat and we are sailing in the same direction, right? And frequency response, I said the object of studying this, all right, and so on. So this is the part 1. So maybe we will have midterm test somewhere around here. And part 2 is this one. So this entirely deals with control, voltage mode control, and current mode control. And this is one typical application of current mode control to offline flyback converters. This is very good stuff, okay, very practical stuff, okay. So probably I cannot finish all of this. If the semester ends around here, then remaining part will be covered next semester, okay. But I want to make sure everybody at this time understand everything I'm talking. So we are in the we are in the same boat and we are going to the same direction, something like that. Okay, so this is kind of a long introduction about this topic number 1. Right. I know you don't have this lecture slide, but this will be posted, okay, at the eeclassroom.org after this class, okay, if everything goes okay. Right. This is the first time I'm using this without any student helping me. Right. I hope everything goes okay. Right. First topic is open loop bug converter. Again, object of studying this is the very basics about the DC power converter for the beginners and some students never exposed to the power electronics, PWM converters. So this is a very good point to start out. Okay, if you need further than this, the below this level, you should go back to the video dealing with the circuit component and the circuit topology of PWM converters. I already introduced that. All right, this is page number 1, and this page is condensed version of description of bug converter. So bug converter, I'll explain the term bug later, but this is ideal step down DC to DC power conversion. Ideal means everything is ideal. We are assuming everything is ideal here. Okay, and the step down means this is the input voltage and this is out voltage. In between, you have something. This out voltage is always lower than this input voltage. So we are stepping down the input voltage and generate the reduced smaller voltage as the output of this converter. So this converter is called step down DC in, DC out converter, power conversion. So power conversion is changing the form of electrical power. You understand the AC and DC, right? The power coming out of the outlet of this wall is AC. But your equipment, most of them requires DC. So you need to change AC to DC, that is called the rectifier. That device performing that function is called the rectifier. Some undergraduate student asked some strange questions. Why there is a DC? You have already DC. Why you are changing DC to another DC? Why you are doing that? Because the voltage level is different. So we have 24 volt of battery. For some equipment, it requires 5 volt. Then you should step down this voltage to 5. Okay. So there are many ways of doing that, but we want to do it without any power loss. So that is not easy. Okay. For the AC, you can change the magnitude of AC easily using just transformer. Transformer will do the job for you, but this to DC power conversion is not that simple. It's simple, but you should study this. Okay. So this is the functional description of ideal step-down DC to DC power conversion. So we have DC input and we have output, and this requires a fixed voltage. Okay. This can be resistive or something else, but the resistive is very rare case. Usually something else, some equipment and something else. Okay. So inductive load, capacitive load, combination of them, or any load, and this DC, and this ideal low-pass filter. Of course, there is no ideal low-pass filter. Just assume this is ideal low-pass filter. Okay. And we have switch. This is called double pole single through switch. Means there is 2 poles. This is called pole A. Pole A is here. This is pole P, and this is through. This is C. Okay. So this switch is connected here or here. Okay. One of 2. It's not hanging like here. This state is not allowed. So this should be connected to this part or this part. So it's called single pole. There is 1 pole in here, and there are 2 throws. Okay, this is throws, this pole. Okay, maybe I mixed the name of this port previously. So this is the correct one. Single pole. SPDT switch. A means active switch, active terminal. Later on, you will see the active switch, MOSFET switch is connected to here, and the P means passive terminal. Passive switch diode will be connected there, and this is common terminal means this is shared by this throw A and B, and this is connected here or here. Always one of them is not hanging like this, and the inductor will be connected here. So this is called the common terminal. So inductor will come in here. Right? Why inductor is coming here? If inductor is connected here and connected here, we have some problem. Inductor current cannot interrupt it instantly. There is just some problem. Voltage spike problem will destroy your system, your circuit. So the inductor should be connected either this one or this one all the time. Okay. So A is active terminal where active switch will be connected. And P is passive terminal. Okay, C is common terminal. Right? So this is connected. Suppose this is connected to A, then voltage Vx, output of this will be this one, Vs. Right? If this switch is connected to the P terminal, the voltage here is shorted, is 0. Okay? So function of this SPDT switch together with this Vs is generating these pulse waveforms. Right? So pulse waveform looks like this. So value of this instant is when this SPDIT switch is connected to the A terminal, the voltage becomes Vs, and the remaining part becomes 0. Okay, so there is some notation. This operation is periodically done. So this is a period, operational period Ts. During this Ts period, this switch C, this common pole is connected to the A through. That is called on time period, T on. And when this is connected to this P, it's called off time period, T off. So Ts is switching period, and the T on is on time period, and the T off is off time period. And the ratio of between this is on time period divided by Ts is called duty ratio or duty cycle. Don't call it duty. Duty is something else. Many Korean students, they call duty. Duty is something else. Your duty is to study this. Okay? This is duty cycle or duty ratio of this switch, SPDIT switch. Obviously, this is one single number between 0 and 1. Okay? If this is 0, so this switch is connected to this pole all the time during the TS, and this is 1, then switch is connected to this. But then this circuit is not working as the DC to DC converter. For the function of the DC to DC conversion, this D should be some number in between these two extreme numbers. And this is defined as D, and the D prime is this one. And the TS is T on plus T off. So using this, so D prime is given by 1 minus D. So in other words, this is D plus D prime is always 1. This looks obvious, but sometimes you will be using this fact in analyzing some complicated things. Then, so this is coming in, and this ideal low pass filter is just filtering this. Filter out this ideally, that means the average value of this, just average value of this will appear this. That is the definition of ideal low pass filter in time domain. Okay, so don't ask why. So this becomes this average value is appearing here, another DC. Then the expression for this is input times this ratio. That is obvious, right? Because this is average value of this. So our voltage of this system is average of this voltage appearing input port of this ideal low pass filter. So this bar means the average operation is performed on this. So this is average value of this. So this and this one becomes D, right? So dVs is the voltage gain of this step-down converter. This is so obvious. Okay, this is time domain interpretation. So this functional block is transferred to this. Then maybe it's very informative to understand this in frequency domain. So same as the previous case, this is the combination of this is functioning as one component. So output of this is, as we have seen, this is this pulse waveforms. So Vs0, this is a Vxt, right? Then you take Laplace transformation of this. Okay, this is the coefficient of the Fourier series analysis, non-Laplace Fourier series. Okay, let me take that back. So forget about Laplace Fourier series. So this component, this is the fundamental frequency component, second harmonic, third harmonic, so on. Okay, so this is decaying like this, and we have ideal low pass filter. What is the definition of ideal low pass filter in frequency domain? In time domain, ideal low pass filter is generating just simply output of this input port to the output. Okay, that is the mathematical definition. And ideal low pass in frequency domain is this one. So now this axis is frequency, omega. This is the frequency, all right? And then this is the gain is then this gain is 1 up to certain frequency. Okay? This frequency is called cutoff frequency. So ideal low pass filter. This is the gain of this filter is just 1 up to this point, and after this frequency, it completely blocks any other component, right? And our assumption is our switching frequency, which is 1 over this switching period, is larger than cutoff frequency. So maybe omega S is here. Okay, so omega C is smaller than omega S, or omega S is larger than omega C. That is our assumption. Then what will happen? Only this DC component. So DC component is somewhere here. You cannot throw this in here. No. Maybe this can be considered as 0, but you cannot throw DC in log scale. Suppose this is something else. So this component is here. So then this cutoff frequency is starting from this and is before the switching frequency. Omega C is here. Then only this part will pass untouched, unattenuated, and all other components will be completely blocked. So output of this is only DC, this component. So you convert this into time domain expression, which is extremely simple. Just DC, and value of DC is D times Vs, which is same as this one. Okay? So this is simply Fourier expansion of this Vx. The Vx has DC component, and it has this Fourier series, first harmonic, second harmonic, so on. And this CO is DC component. It's just average value of Vx, which is and this component is given by this expression. You don't have to worry about this. You don't have to derive this. Just take this. Okay. Finding out this is not a power electrons. That's something else. Okay. Don't spend on this. And this is, if n is 1, then that is the coefficient of the first harmonic. If n is 2, then that is the coefficient of the second harmonic. And this d here is Dewey ratio, and this 2 pi is in terms of degree. You may use this number in terms of radian per sec. Then you can use this, right? And then output is this one. So this C now is same as this one, same as previous one. So this is ideal step down this power conversion. So ideally, this our voltage is pure DC if we use ideal low pass filter. Okay, so we call it ideal step down DC to DC power conversion. So this one is obvious, ideal, because we assume this ideal low pass filter. So everything is ideal, but nothing is ideal in real world. So this is just conceptual things, but there are some practical converter, which is the most popular converter, and that practical converter is called Buck converter. Okay, Buck means many things. Then Buck means many things. The U.S. dollar is called Buck, and the animal, this deer, is called Buck sometimes. Okay. This is the ideal DC to DC power conversion circuit. Realized practical physical device is called buck converter. So this part is this SPDT switch is implemented as a connection of combination of this MOSFET switch and diode. MOSFET switch is here, diode here, and the connection of this is functions as SPDT switch. So maybe this is something functional description of this. This is APC, and this is SPDT switch. And ideal low pass filter is implemented using this LC. Assume this R is load resistor, and the combination of these three components functions as that function says. Actually, it is second order low pass filter, right? So this ideal DC-to-DC power conversion is practically implemented with this SPD switch, and the second order low pass filter is called the buck converter. Okay, so this is the waveforms of this. This is the gate source voltage. MOSFET is 3-terminal device. If gate source voltage is sufficiently larger than threshold voltage, the channel will be created between this and this. So this circuit is shorted. Okay, practically this is shorted. Then this voltage will appear here. Then this voltage will reverse bias this, and bias is turned off. Okay, so with this, during this period, this switch is connected, this is open. That is same, exactly same as this pole is connected to this A pole. Same situation. Okay. Now this switch is turned off. When switch is turned on, later on you will see some current is developed here. So this is cut off of the tree. Then this current will maintain continuity. That is the one important property of inductor. Inductor keeps this continuity of its current, if possible. There is a way of doing that. That inductor current it will do that. Okay. So this current is cut. Inductor current goes here, come back here. There is a low return path. This is off. Then that current turns on this diode and create this path. It's called the freewheeling path. Okay, and that diode is called the freewheeling diode. So with this kind of operation, so then this common throw is connected this P pole, so which is the function of this SPD switch. Okay, so this is function as this, and this functions as low pass filter. So with this type of voltage will be generated, same as the previous case. Okay, very similar to that, but not exactly same as the previous one because of some practical limitation of this device. Maybe there is some voltage drop, small voltage drop, and small resistor. So assume everything is ideal. Okay, then this voltage will be applied to this low pass filter. Okay, then output of low pass filter will smooth out these waveforms. Then, but final value, as final waveform is something like this. The DC value of is average value of it, but there is some component, this sinusoidal-like component. This is called the ripple. Okay, because this is a non-ideal low-pass filter, just a practical second-order filter. So there is a final ripple. So this average value of this output voltage is, of course, this is dVs. So there are some ripple component. So this VOT is actually sum of two components. This is a VO. Okay, average value of this is VO. VO plus del VOT. Okay, this is the some varying component, AC component of our voltage contained in the our voltage, because non-ideal filtering characteristic of this practical second order filter. Right? So this is called the ripple. Okay, so if you go to the lake or pond, there is water. So if you look, that water at distance looks like this horizontal line, but if go to the close to it, then you will see something is fluctuating. This is called the ripple. Okay, so ripple. You want to reduce this ripple. You want to have this very as small as possible. So to understand that, you need to study the transfer function of this. Okay, if you find transfer function of this and you think about the frequency response of this, okay, frequency response of this this second order filter is response to the sinusoidal wave of applied to the input. Okay, assume this is the sinusoidal waveforms or collection of the sinusoidal waveforms. Okay, then what will appear here is called the frequency response of this system. So from that you can evaluate the magnitude of the ripple. For that purpose, we think about the transfer function in between this and this. Extremely simple. So this is the LCR circuit, second order circuit. So this is transfer function, just ratio of the impedances. Then this is the frequency response expression of this transfer function. It starts from 1 plus S divided something plus S squared divided something squared. Okay, this is standard format. And this omega naught, which is 1 over 1 divided by square root LC, is called pole frequency or double pole frequency. Don't call it resonant frequency. Resonant frequency is something else. Okay, this is a pole frequency. And this Q defined here is its expression. Its expression depends on structure of this. For this particular structure, expression is this, and this is called the quality factor. Okay, quality factor means quality of something. What kind of quality we are talking about here? Quality as an energy storage element of this. Okay, quality factor will be this one will be relatively small because there is a resistor which consumes the power. If this resistor is missing, this quality factor becomes infinity because there is no power consumed in between. Okay, so this is this definition. This definition is very important in resonant power conversion, but we are not interested in this that much. But it's just called quality factor. And there is another expression in control systems. They prefer use the definition of the zeta. Zeta is something similar to this, but the motivation of defining this Q and the zeta is entirely different. This is a relationship between these. Okay, so don't confuse with this. Q here is quality factor. Okay, this is the for notation for power electronics. For something else, like the control theory, they are using the zeta. Right? Then zeta is 1 divided by 2Q. Okay. All right. So with this is the transfer function. So frequency domain ripple analysis using this transfer function. Let me explain the concept of this first, and some details will come later. Okay. This is a transfer function of Bode plot of frequency response of this transfer function. Okay. I'm using term frequency response and the Bode plot. So probably all of you are familiar with these terms from other courses. Okay. So this is asymptotic plot. So before this omega naught double pole frequency, this gain is just 1, which is 0 dB. So it starts from 0 dB. And this omega naught is pole frequency determined by this. And starting from this pole frequency, this slope is decaying minus 40 dB per decade. Because this is the second order filter, if this is the first order filter, LR filter, then this slope will be this one, minus 20 dB per decade. So we call it minus 2 slope. Minus 2 slope means minus 40 dB per decade. Minus 3 slope means minus 6 dB. Minus 4, minus 40 dB per decade, something like that. Okay, it's a very convenient notation of representing this slope. So we don't use this one, just to use number minus 2. Okay, and there is this is omega S switching frequency is here. This is the second harmonics twice of switching frequency, and this is log scale. This is 10 times of the switching frequency. As I said, this switching frequency is beyond this double frequency. Then we have attenuation here. So at this frequency, at the switching frequency, the switching frequency component, fundamental component, will be attenuated by this amount. It's obvious, right? Because this is slope, decaying slope, okay? And this is the ratio of this switching frequency. And this is resonant frequency. Maybe this resonant frequency is 10 times of this, switching frequency is 10 times of this resonant frequency. Then this attenuation will be minus 40 dB, which is attenuation of 100 times, okay? For this second harmonic, we have this, with just 2 is coming here, okay? From this, we have this generalized expression. In the past, some student, undergraduate student, they think this is very complicated and something advanced or some fancy things. Not at all, okay? This is just this substitution of something. So this is a Fourier series representation of Vxt. Here, this C naught is this component. This component will be passed without any change. It remains the same. And this sinusoidal component will be attenuated by this filter. And we have a relationship between this and this attenuation factor. Okay? So this is the Cn prime is attenuated version of this coefficient. Coefficient of this out voltage, which is attenuated version of Vxt. So Cn prime is Cn, simply Cn times attenuation factor. Okay? So for the n omega s, n is integer. Okay? For the n 1, 2, 3, then we have this is attenuation factor. Right? This is not complicated at all. It looks complicated, but conceptually this is something extremely obvious, right? Because you have this number in log scale, so we need to change the log scale attenuation to linear scale. This is log to this exponential conversion. Okay, this is middle school stuff. So you have this. So we have this expression. And the Cn, this is a Fourier series coefficient of this rectangular waveforms, and this is given. So this is given, and n is known. Then we have this attenuation factor. So we just multiply them out. Then you have the coefficient component, coefficient of the harmonic component in the output, and from that you can evaluate the ripple component. Okay. Usually you don't have to this. But to understand this the theoretical background about this one, this DC power conversion, maybe this practice is necessary. Okay? All right. In the lecture slide, I will add something here. Okay? I don't want to repeat the tedious thing here. But somehow I write down. Then you can immediately know the meaning of that expression. Okay? So I add something because we have a long story ahead of us. So we needed to speed up. Okay? All right. Let me give one example. This is buck converter. Input voltage. And this is this MOSFET drive signal. That MOSFET is turned on, this is turned off. Then MOSFET is turned off, this diode turns on. You already know this, right? So with this, the ratio of this is what? D. So here, D is this. 5 divided by 20 is this number, all right? Then our voltage is, DC component of our voltage is input voltage times duty ratio, which is 4, okay? Then our voltage will be something similar to this time axis. This value is obviously 4 volt, but we will have some ripple component here. You want to reduce this, del VOT, fluctuation component of this should be minimized. And we have this value, omega naught, is given by this. And switching frequency is inverse of this. Which one is it? This. Okay, you need 2 pi in this unit, omega s unit, which is this one. This one, as I said previously. And we calculate the harmonic component of our voltage. This is the DC component, is 4, all right? And the component of fundamental component contained in our voltage is this one. This is C1, is given by the Fourier series of Vxt. This is known, and this is what? Attenuation factor, okay? And you know everything. So this D is this one, and you calculate out this. So this number, this is the magnitude of the C1 prime, which is fundamental component of our voltage induced by the fundamental component of this Vxt. Okay? And second term, third term, fourth, fifth, so on, so on, so on. Right? This is the simulate waveform of our voltage. Okay, this is exact simulation using PSpice or CAD. In the past, it was that the software was called PSpice. Now it is called ORCAD, but they are using the same machine, same engine for the numerical integration. So they are same thing. So this voltage should be, average voltage should be 4 exactly, right? But in the PSpice, they are using the physical model of diode for the diode. So there is no ideal diode in PSpice. So there is some voltage drop or something. Whatever small it might be, it causes some error. So this value, middle of this should be 4. Okay? This error is because we are using the PSpice. We use some ideal diode, it will be 4. Okay? This is the AC component. This component is something similar to very simple sinusoidal wave of at the frequency, no, switching frequency. Right? That means only fundamental component is appearing at our voltage. Why is that? You calculate this, and you repeat this. There are 2 important facts here. One is this DC component is much larger than this harmonic coefficient of our voltage. Practically, this is a DC 4 volt. This of the 4 volt. Okay. This is 10 times lower than that. Just ignore that. This is nothing. All right. So even though you are using this practical device and the practical value of this component, this output is practically same as the ideal power conversion. Okay, that is very important. So don't think ideal power conversion is something imaginary. That is not true. You can easily implement this with negligible ripple component very easily. Okay, that is one thing. So C naught is much larger than this output coefficient of higher order harmonic. That means output voltage is practically 4 volt. Right? Another important factor is when you compare this C1 prime, C2 prime, C3 prime, this is the higher order coefficient of harmonic component in the output voltage, but C1 is much larger than this one. It becomes smaller, further smaller. Okay? Just consider this. Just because this is about 10 times or 5 times. Just ignore all of them. Okay? Then consider this output voltage at the first harmonic frequency. Okay? At the switching frequency, magnetic expression is that Ci prime sine omega st at the frequency, and there are some phase delay, but forget about phase. Okay, phase is nothing here. Then our voltage will be like this. There is a DC, pure DC, and this fundamental component is superimposed on that, and this magnitude of this is del VOT is 2 times C1 prime. This is obvious, right? Assume you forget about all the harmonics and just consider this fundamental one. And you know this, and this is the predicted magnitude of ripple component. based on this simplified analysis of this simple second order low pass filter, if this is the magnitude is 7.8 millivolt, and this is what? This is 4 millivolt, very similar to that. Okay, so this is the exact expression, almost the exact expression. That means our voltage, it can be considered as a DC here. Okay, so you achieve DC to DC power conversion using practical switch, semiconductor switch, and this second order low pass filter. Okay, let me say one thing. Okay, so for the step down DC to DC power conversion, obviously we need this SPDT switch. Load of this is transforming this DC to this pulse type waveform. Okay, and you need to have what? Low pass filter for the averaging of this. So any type of low pass filter can appear here. This is a standard second order low pass filter. Maybe there is a first order low pass filter or a third order, fourth order, cascade low pass filter. There are many combinations of low pass filter. All of them is okay, right? So any low pass filter is coming here, right? And averaging of this. So input of low pass filter is this one, Vs, something like this, right? Then output, initially, input is high, then output will try to follow this with some delay. At this point, this input is reduced to 0. It tries to follow this, like this, and try this, and something like this. And eventually, in steady state, it will approach for this. This is the averaging effect of the low pass filter. In terms of frequency domain, it attenuates higher order harmonics. In terms of time domain interpretation, it takes the average value of it. Okay, with some finite ripple because of these characteristics. So ideal low pass filter. So directly the average value of this is appearing. That is the ideal case. Right? Okay, I think I should finish up this one here. I should return everything in time until 6 o'clock. Okay. Tomorrow I'll ask about the LMS side, right? And I'll upload the lecture slide, just part of it, topic 1 or 2, in the e-classroom tonight, along with this post-lecture slide and the post-lecture video. Okay? All right. Okay. Thank you.